So question 10 from the trial exam is paper 1 2020, question 14. We've got a large spherical balloon is deflating. We've got time in seconds, radius in centimeters, and volume in centimeters cubed. So the volume of the balloon is modeled as decreasing at a constant rate. So that's important. Okay, that's telling us a derivative. If the volume of the balloon is decreasing at a constant rate, we can state that dV by dt, which is the change in volume or the rate of change of the volume, is decreasing. So to show that it is decreasing, I'm going to put a negative sign there and a C, and I'm going to show that C has to be positive in order to force that rate of change to be a decrease. Okay, we want it to be negative. So we'll say where C is greater than 0 and constant. Okay, so that's important. The rest of that first two sentences is just talking about the shape. So we can say that the volume of a sphere is 4/3 pi r cubed. And we've defined the units in which the r and the v and the t are measured. So we have to show that the rate of change of the radius is this differential equation right here. So once again, if we've got formulas that we're going to be using, the best thing to do is to differentiate them. So this is going to differentiate. So it's going to be dv over dr, which is going to be 4 pi r squared. And we've done that a few times in class. Now then, let's just build our summary of information. So we've got dv by dr right there. Okay, from the formula of the volume. We also were told that dv by dt is equal to some negative constant. What we want to find is dr by dt. So how do we construct that? Well, dr by dt would have to be dr over something multiplied by something over dt. It's pretty obvious what's going to go in there. It's got to be dv in both cases because that's what information has been provided. So we have to do dr over dv, which is 1 over this thing, multiplied by the derivative that we wrote down earlier. So let's have a look. This is going to equal, just running out of space again, dr over dv, so that's going to be 1 over 4 pi r squared multiplied by dv by dt, which is going to be negative c. So this is negative c over 4 pi r squared. Now, looking closely at this, the 4 pi and the c are constant. And not only that, they are all positive. We define c as positive right here. 4 and pi are both positive numbers. So the negative sign in front of it forces this entire thing to be negative because the r squared is also positive because it's a square number. So we know this has to be a negative derivative, so it's a rate of decrease. And we can also state that this is equal to minus k over r squared, where k is equal to c over 4 pi. Remember, you can redefine constants as much as you want. Okay, c and 4 pi are constants. If you do a constant divided by a constant, that is also a constant. So we've shown that without too much trouble. We're then given some initial conditions and some boundary conditions. So initial conditions, we're given the initial radius of the balloon is 40 centimeters. So in other words, when t equals 0, r equals 40. And also, we're told that when t equals 5, r is equal to 20. Now, We're going to use those in a moment because we're going to have to solve this differential equation. So those are the conditions that we're going to sub in to hopefully eliminate the constants or put actual values to those constants. Now, if the first part doesn't go too well, you can still do the second part because the differential equation is given to you. It was a show that question. We've also got the conditions. So to solve the differential equation, we need to separate out variables. So we need the R variables on the left and the T variables on the right. So I'm going to have to multiply both sides by R squared here. So we're going to have R squared dr is going to equal negative k dt. Okay. Now, multiplying both sides by r squared, I've also multiplied both sides by dt. So we now have nominated the left for the r variable and the right for the t variable, and the constant can stay where it is. We can now integrate both sides. So I'm going to put my integral sign on. I'm going to put it around the dt and after the constant, because the constant may interfere with that integral or make it more complicated. So let's integrate. So we add 1 to the power, divide by the new power, and we integrate dt with respect, we integrate 1 with respect to t, that's just going to be t, plus the constant of integration. Okay, that's our general solution. Now, we are given these initial conditions. Okay, we know that when t equals 0, r equals 40. So I'm just going to make a fuss over this. This is the general solution right here. Okay, so the integration wasn't too bad. Let's sub in the conditions. So when t equals 0, r equals 40, initial radius of the balloon, we're going to get 40 cubed over 3 is equal to, now minus kt, obviously t is 0, so that's just going to be c. So that's our c, which means that c is going to be 64,000 over 3. And I don't think that simplifies. Okay. Now, let's just rewrite our general solution. So we now have r cubed over 3 is now equal to minus kt plus 64,000 over 3. So it might be a good idea now to multiply by 3 to clear those thirds. So therefore, r cubed is going to equal negative 3kt plus 64,000. So we now need to find k. So let's apply our next conditions. We know that when t equals 5, I wrote them down up here earlier, r equals 20. So let's sub those in. So 20 cubed is going to equal minus 3k multiplied by 5 plus 64,000. Okay. So let's just figure this out on our calculator. So 20 cubed, which is 8,000. Now we're going to have to subtract 64,000 from both sides. Okay, so that gives us that. And then we're going to have to divide by negative 15, which is obviously minus 3 times 5. Okay, and that's going to give us 112, sorry, I beg your pardon, 11,200 over 3. So back to that. We have got 11200 over 3, which is equal to k. Now, we can now write down our particular solution. So I'm going to move over to the left-hand side now. So particular solution, which is what we wanted. is going to be as follows. So it's r cubed is equal to, now it's going to be minus 3k. So if I times the k by -3, that's going to be negative 112. I keep saying that, 11,200 t plus 64,000. Okay, so we now have a function for the radius in terms of time. Okay, so that completes part B. For part C, it says find the limitation on the values of t for which the equation in part B is valid. Well, obviously time is going to be greater than 0, but not only that, for this to be valid, the radius also has to be greater than 0. Otherwise, there's no sphere. Okay, the balloon doesn't exist. So if we put that limitation on there, we have that negative 112. I keep saying that, it's so annoying. 11,200 t plus 64000 is greater than 0. Okay, because that's, if r is greater than 0, r cubed must also be greater than 0. If we rearrange, we get 64,000 has to be strictly greater than 11,200 t. And if we divide through, we get, I'm just going to move this out of the way a little bit. So let's cancel, and then we do 6, 4, 1, 2, 3, divide by 1, 1, 2, 0, 0, 40 over 7. All right. And it's not letting me move it for some reason. There we go. So that's 40 over 7. Now that's in seconds, right? So the t, the value of time, this model only works for values of t between obviously 0 and 40 over 7 seconds.